Hello everybody, welcome to this video. In the previous video, we have learned that differentiation or differentiating will actually give us the gradient function. So today in this video we are going to really go into what are the steps of differentiating. So we start with polynomials first because they are the easiest to differentiate. Okay, so if you can recall, polynomials, they are of this form: plus a1 x1 plus a2 x2 plus blah 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 blah, so on and so forth. Okay, so you have learned this in the Sec 3 course, so I'm not going to cover it anymore. You should know it very well. So as I have said, today we will be learning how to differentiate polynomials. Okay, polynomials with power n, for example, of such form x to the power of n, and also find the derivative of x to the power of n plus x to the power of m. So plus or minus actually. So today we will actually learn how to do something like this. Okay? Or let's say if y equals to x to the power of n, and then we want to find dy dx. So what are the steps? Today we are going to learn the steps. Okay? As well as those where you add them together. So polynomial forms. Okay? Okay, so as I've said, differentiating polynomials is actually very easy. So for example, let's say if I have a function just y equals to x to the power of n, then my dy dx, or my gradient function, would just be bringing down the power of n and then reducing the power by 1. So I repeat, the dy dx would just be multiplying by the previous power followed by reducing the power by 1. Okay, so if let's say y is equals to x to the power of n, then dy dx is just initially the coefficient over here is 1. So now I multiply n in, I get n x. So the new power would just be this old power minus 1. Okay, same goes for, let's say if I have a whole long chain of polynomials. Okay, they are added together. Okay, then you just have to do the same for the individual terms. For example, let's say y is equals to x to the power of n plus x to the power of m. So dy dx would just be multiplying the previous power to the coefficient and reducing the power by 1. So same goes for this case with the m. Okay, so it is the gradient of the original function at a particular x coordinate. We have learned this in the previous video. Okay, so now let's put what we have learned into an example. So for example, if I have to differentiate y equals to x to the power of 5. Okay, so let me just sketch the graph of y to the power of 5 for x is more than 0. Okay, so this is the graph of y, this is the graph of x. Okay, I mean the y-axis and the x-axis. So y is equals to x to the power of 5. So you want to find the gradient function, we want to differentiate it, so we want to find dy dx. And dy dx is just multiplying the previous power by the coefficient. So initially the coefficient is 1 here. So multiplying it, we get 5 x, and the new power would just be the old power minus 1. So 5 minus 1 would be 4. Okay, so dy dx, the gradient function, is 5x to the power of 4. Okay, so for example, let's say if it's this, So I can also plot the graph. This one is less steep, okay, but it's still a curve. So this is 5x to the power of 4. Okay, take note that now this axis here would be dy dx. So this is the graph of the gradient function against x. Okay, so for example, if I want to find the gradient at x equals to 2, so let me come to this graph and I go to x equals to 2. So what I really actually have to do is, let me just use another color, is I have to actually find the gradient line here. Okay, by right this should be the one spot that touch. Okay, and then I will have to find the gradient using our formula. So we have our formula y1 minus y2 minus y1 over x2 minus x1. Okay, so this is how we find our gradient initially. But now we have the gradient function. All we have to do is to find the value at x equals to 2. So for example, I find x equals to 2. I will just have to take this value here. So for example, this value here I call a. Okay, so a would actually just be equals to the gradient over here. Okay, so what's this value of a? Let us work it out. So we have to find it at x equals to 2. So it is just 5. X is now 2 to the power of 4, which is equals to 5 times 2 to the power of 4 is 16. So this will be actually 80. Okay, so the value of a here is actually equals to 80. So let me just say this is 80. Okay, so if I were to actually use the graph method to find the gradient, I would and use the formula to find the gradient, I would also get 80 from here. Okay, but of course then I have to do it on graph paper and it's very troublesome. Okay, so we have found the value. Now we have found the value at x equals to 2. Okay, so the next thing we want to do now is to find the second derivative. So to find the second derivative, what it actually means is to find the derivative of the gradient function. Okay, and we want to find it at x equals to 1. So what we actually want to find on the graph is this gradient here at 1. Okay, so the second part of the question. Okay, so this is what we want to find now. So we could draw this on graph paper and find the gradient, or we could also make use of what we know now to find to find the gradient over here. So it is not b. I made a mistake here. Okay, so what I actually want to find, b should be on this graph, the d2y dx square graph. Against x. Okay, so before I draw the graph, maybe what I can do is, let me find d2y dx square first. So d2y dx square is actually, since dy dx, it's 5x to the power of 4. So d2y dx square is just differentiating. So this is the differentiating sign. Differentiating my dy dx one more time. Okay, so what do I have to do? I have to multiply the coefficient by the power, so to get 20, and then reduce the power by 1. So 4 minus 1 would be 3. Okay, so the graph of d2y dx square is actually a x cubed graph. So the x cubed graph would also look like this, but it's less steep than this and this. Okay, so remember I actually wanted to find the gradient over here, but let's say with this graph, all I have to do is to find the value of d2y dx squared, and it will be equals to this gradient I find using this formula as well. Okay, so this value here would be, so let's say if I sub 1 into, let's say I sub 1 into here, I would get, so d2y dx squared at x equals to 1, at x equals to 1 would then just be equals to 20 times 1 cube, which is 20. So this value here is 20. So if I were to use the gradient method to find this, using a graph paper, I would also expect to get 20. So you see the benefits of the differentiating function actually. Okay? Okay, let's move on to another example. So now I would have to find the derivative of y equals to x squared plus x plus 1. So I do not need to find the gradient, I just need to find the derivative. So I don't have any points to sub in. Okay? So this is a x squared graph. So let me just plot out how the graph would look like. Okay, intersects at 1. Okay, and it does not cut, so it will look something of this form. Okay, so to find the dy dx, I will have to do it for each term. Okay, take note this 1 here is actually 1 times x to the power of 0. This term is actually 1. Okay, so x squared after differentiate, so I can differentiate it term by term. Okay, so x squared after differentiating, coefficient is 1, bring down the power to x. Okay, x is just, after differentiating, is just 1. Okay, and this one, x to the power of 0, so it's a constant. Now if we bring down 0, if we multiply by 0, we will always get 0. So take note, so this is a constant term. Okay, and constant term have 0 derivative. 0 as its derivative. Okay, so take note. So constant term always after differentiating is 0. Okay, so actually plus 0. So we don't need to write that down. Okay, so this is our gradient function. So let us plot our gradient function. Gradient function dy dx and x. Okay, so we know how to plot this. This is actually very simple. We just have to go here. This is minus half, and this is 1. Okay, so this is our gradient function, dy dx equals to 2x plus 1. So that's all, very simple. So if you were to want to find the gradient of any points over here, we just have to get the x coordinate and then just find the value over here using the same corresponding x coordinate, and we will be able to get the gradient here just by reading off this graph. Okay, so in summary, for any function y is equals to x to the power of n, the dy dx would just be n x to the power n minus 1. Okay, and for polynomial terms which you add, you can do it term by term. Okay, this is a recap from the previous video that the gradient of the original function at the particular x coordinate, it's actually just the dy dx. Okay, so we have learned how to do it in the 2 examples that we have seen. Okay, so sums of different polynomials, we can just differentiate it term by term. Okay, here are some practice questions. If you are using PenPack A-Maths textbook, you can try the level 1 questions and the level 2 questions. Okay, the level 1 questions are very simple, just normal differentiating, while the level 2 questions involve certain applications as well as being not so straightforward. Okay, With that, I thank you for watching this video. Thank you very much.